So, okay, general topics: mechanical oscillations and waves, physical acoustic, logarithmic scale, and practical. At the beginning, what does actually sound mean, and what does how does it propagate in the medium, and so on? Yeah, general terms, we should look to the sound as a mechanical wave. Mechanical, it means it do some vibration. That's why I would like to say, as a sound, the topic of the sound is quite close to the topic of the oscillation from the previous time. That's why the both levels are pretty close, yeah, from the general point of meaning. But obviously, if you're thinking about sound, this is something more obvious for us than just thinking of mathematical oscillation. Take a look. This picture describes that sound can propagate only in the medium where some particle exists. Do you know how do we call the medium? There were no particles at all. How do we call such space?
Vacuum.
Vacuum, exactly. Yeah? Vacuum is an empty space. And if in a colloquium you have a question about do you how do you think sound, does sound able to propagate in a vacuum? The answer is no, absolutely no, because no particles. Sound needs some oscillations. Sound needs some particles, and generally it is air molecules which allows sound to propagate the medium. And you see, this red point, what does it show? It shows that sound actually do not move particles from the point A to point B. The particles do not change its position by itself. They just work as an energy transformer. They just bring an energy from one point to another. But you see, this red point is just works on an oscillator. They move towards and back, towards and back. Therefore, sound can propagate and we can hear each other, and me as well. Okay, here is a quite good video which really gives information how does vacuum can help us to isolate environment from the sound, and the next slide as well. But let's look at this video where you can see that how the bell stops ringing when we use a vacuum. And if you have a vacuum pump, you can try to repeat this experiment at home. Yeah, it's actually nothing complicated, but I would like to say it looks amazing how we can prove the physics. Yeah, let's have a look and then discuss about it. Now we will release the tube and let the oxygen flow into the chamber, and after a while you will hear the sound again. To prove that sound needs particles. Right. Okay. See, this is a up, and as I usually remind, if you don't know the physics, sorry, what is it goes wrong? I think maybe okay. Let's repeat, yeah, and I will share with the sound. Now you can hear sound of the bell, because oxygen fills the chamber. Yeah? Nice, yeah, nice. And as I usually said, if you don't know the physics, everything becomes nitrogen neutral. Yeah? In physics, explain a lot of interesting experiments, like this with the sound. Yeah? Okay. So, I forgot to. Sorry, I forgot to ask who is here. Yeah, who is present? Ellen, are you here?
Yeah, I'm here. Hi.
Yeah, right. Nice to meet you. I want to see you as well. So, Lisa.
Yes, I'm here too.
And what? No, sorry. And what kind of name you prefer? Charlotte or Elizabeth or Mary?
It's Charlotte, but we're two Charlotte, so I'll be Lottie and the other Charlotte will be Charlotte.
Charlotte. Okay. Okay. Leah.
Yes, I'm here. Hey.
Yeah. Charlotte. Sophie.
Yeah, I'm here too.
Judith.
Yes, good morning.
Christina. Good morning, Christina. Where is she? She's sleeping. Could you give information through WhatsApp maybe?
I think
already start our lecture.
I think you asked about Christina.
Christina, fine.
Yes. Well, she got a study place offer in Germany, so she's exmatriculated.
Okay.
Yes.
Thank you very much for information. Yeah. Jan.
I'm here.
Oh, nice to meet you, Linda.
I'm here too.
Goran.
Yes.
And Leticia.
Yes.
Okay, nice to meet you. Okay, yes, any questions so far about sound? Any question? If you have any questions, please you can also give information to chat. Yeah? So let's go further. course, I understand it's quite hard to study such early morning, yeah, but you can look from the on the other hand, yeah. You now have a lecture, and then all the day you are free, yeah. You can go walk. You can go. It's a. You have any lecture today, Julian? You have any lecture?
Sorry, what?
You have any lecture during the day? Today? Or only
Yeah, we have bioethics.
Bio. It's easier than physics, I guess, no? You don't need to understand so much complicated facts. Okay, so let's continue. Isolation, yeah? Isolation, you can do the isolation. For example, you can see the glass, and if you if you use the two plates of glass, and then space between them fill with a vacuum, or just to remove all air molecules, then you can observe the sound, because you know vacuum cannot conduct sound. Obviously, no sound at all. Next one is a quite good illustration how sound actually creates the vibration, huge amount of air molecules. Let's have a look. And it proves the sound is just vibration of the air molecules, or oscillation of the air molecules. You can also open on your own screens, and you can play with the frequency. Take a look. We will take a small frequency, or just about 1 or 2 hertz, yeah? Or 1, 2 oscillations per second. Then we increase the frequency and have a look what kind of waves and how interestingly waves propagate in the medium. Yeah? And that's happening if you, for example, create the noise. If you hit something, or if you're speaking very loud, yeah. And let's have a look further. If you increase the frequency to the high level, you see how interestingly air molecules will oscillate. And that's why, for example, if you listen to music too loud, you can feel even vibration in the air. Yeah? That's what's visualized with such animation, yeah? Tuning forth and sound wave. Okay. So next one, how do we create the sound? How do we create the sound? With all vocal cords. Yeah. If we need to produce a voice, if we need to speak, first of all, we need an air. We need to breathe. Yeah. And that's why in some emergency situation or some emergency case, if doctors, you can see this in every in a lot of movies where some car accident, for example, happens. Yeah? When doctors are trying to speak with the patient, they can't speak, or they even can't to do any sound, because in the car accident, if they're under the shock, they're hard to breathe. Yeah? And if you can't breathe, you don't have an air, you can't produce the sound. And that's why doctors are constantly reminded, please speak with us, tell me something, yeah, or yeah. It means that patients are still alive, are still under the consciousness, and it can breathe. If they can't, if, for example, somebody can't breathe, they can't speak as well. Yeah? Because you need to breathe. But first you need the air, and then you can speak. Yeah? Because air then pushes through a very small space between them, and makes the covering of the vocal cord or fold known as the force to vibrate. Okay? And this causes venturi effect. Okay? And as air passes through the constriction, it speeds up and creates a suction in its way. Okay? And this suction down in the future, and also from each vocal cord, we which means in the midline only to be pushed aside by more air from the line. Okay? Means to be the air in order to push the sound. And this cycle creates a repeating undulation, okay, which is known as mechanical wave. Mechanical wave. Okay? That's the melody. Here you can see. Actually, this is something similar what we are going to look on an oscillation level. Okay? You saw it also when we spoke about oscillation. Okay? This is how we create the sound. And for more information, of course, it's you need to again observe the video from the oscillation. Included in implementation of oscillation. Okay. Yeah, and a little bit about parameters regarding to wave, because sound is a wave. Period. Time when oscillation occurs. Wavelength. Velocity. Velocity is important when you speak about different mediums. Yeah? For example, sound always will be faster in, for example, some metal or some iron than in air, because the atom is more compressed in the metal. Therefore, the sound can produce faster. Frequency, 1 oscillation per second. Hertz. Also, frequency is equal 1 divided by period. Yeah? And amplitude of the wave or distance. Amplitude is the distance from the equilibrium point of the wave. Amplitude usually is described as a loudness of sound. How loud is the sound? It means the amplitude will be bigger. Okay? Amplitude and loudness is similar regarding sound. Here's a couple of questions in order to a little bit give you a short practice. The frequency of sound wave is what you hear. Sorry, what you hear understand as a pitch. Okay. Now the question is how do you understand the frequency? Which wave to the higher frequency? Which one? Which case or which of these people describe the higher frequency?
Is it A, because it's way faster?
Yeah, it oscillates faster. If you imagine that one of every of this picture is one period in time, then a lot of oscillation in one period of time is in case of A. Okay? It means higher frequency. Now the question is which sound is the higher pitch? How do you understand which? What does it mean a pitch?
I think the higher the frequency, the higher the pitch.
Exactly. Pitch and frequency is related to each other. Yeah? It means as higher the frequency, higher the pitch. Yeah? This term is important to understand regarding sound. And we will now listen. I think this also sound generator is quite nice, but I prefer to show you this one, because this is you can listen from 20 Hz to 20 kilohertz. Yeah, this is human hearing range. previous video, you can adjust the frequency. And sometimes it's not so convenient because you just adjust a couple of frequencies. That's it. I just noticed that when I start playing this video, be ready to adjust your sound, adjust your loudness on computer, because sometimes the sound becomes disgusting and the sound becomes terrible for your ears. And yesterday, one student told me, "Oh, stop, professor, stop the sound." Just because the sound perception is absolutely subjective. Yeah? For somebody, it's easy to listen. For somebody, you want to run away. Yeah? But just decrease the loudness, and then it will be okay. If you can't listen, just switch on off the sound. Yeah, but I want to show you the full spectrum. Some of these is not so. This is a pleasure sound for our ear. But let's listen, and you will see what I'm speaking about. Yeah? It's just a spectrum of human hearing rate. Full spectrum. Take a look. It's beginning. We can hear the sound from 20 hertz to up here, 20 kilohertz. But a lot of people actually, from my experience, shows that when we're doing this lab on the class, I allow students to start your measurement with 30 hertz because, from my point of view, the more people, biggest part of the humans can't recognize 20 hertz. This is like not a sound, it's like a silent vibration. It's like a, I don't know. In real life, you such sound can hear when you drive by car. You just hear the engine and feel vibrations. Yeah? And this is like something like this. Only vibrations is not a sound. That's why listen carefully, and probably over the 50 hertz you hear the vibration. I will share this computer sound as well. You see, over 17,000 hertz, we already do not hear anything. Okay? Actually, I would like to say our normal range. Yeah, you see, one thing, adjust your volume. Okay? That's what I told you about. It's important because otherwise you can't listen much sometimes terrible sound. About loudness, we will speak a little bit later. Human hearing range. Humans can hear the sound from 20 hertz until 20 kilohertz or 20,000 hertz. Before ultrasound, this is, as I told you, like vibration. It's not like purely sound, but vibration. And the infrasound, for example, elephants use infrasound in order to communicate with each other at distances as long as 20 kilometers, for example. And they can communicate with this small vibration. Yeah. Now, infrasound you can also hear when you don't hear it, you can feel it when you're sitting in a car. You can feel the vibration, but actually we can't hear it. But infrasound used in medicine, could be used in medicine, and it could be, it also can be unhealthy for us. With headache, become tired under infrasound, up to the 20 kilohertz ultrasound. Ultrasound, I'm absolutely sure if you heard about it, that ultrasound used for medicine, especially for to investigate pregnancy, pregnant women, and unborn child, and so on. Yeah. So, and okay, yeah, and ultrasound. We have a separate lecture about ultrasound. That's why about ultrasound we will speak more in the next lecture. I think in the next or week after lecture. Okay? So that's why about this type of sound we don't speak now. I just mentioned that, for example, dolphins also can use ultrasound in order to communicate with each other. And in medicine, huge application in medicine. Here's the question. Your audio is very difficult to understand. Yeah, sorry. I know where's the problem. Because if I share computer sound, I don't know why, but it becomes hard to understand. Yeah? Yeah. Now, I hope it's better. Yeah. I hope it's better. I think something with an internet, if I share also the sound, maybe it becomes too hard to transform. I don't know. Okay. The amplitudes. The amplitude is equal to loudness. The amplitude is equal to loudness. Yeah. Actually, it describes the height of the wave. Yeah. Tone generator we already listened. Here you could see louder sound, means waves is higher, and softer sound. Amplitude, either loudness, is measured in decibels. And here you could see the several cases where maybe from your experiments what kind of sound it could produce. Yeah, and the loudness of sound as well. And for instance, if you want to practice with a gun, you must use specific earphones, which provides safety from your hearing system. Yeah, or which prevents your hearing system from the external damages, because gunshot is a quite loud sound, and our eardrum eardrums, it's too hard to tolerate such sound, and therefore we need to prevent it. Yeah, or jet engine, or live rock content, and so on. How do you think? Where's the final point, which is comfortable for us, or which is normal for us? Where is the final point regarding to loudness? How do you think? Do you have any ideas about that? For example, have you ever been in a live rock concert? Leticia, have you ever been? How do you feel in such concerts?
Well, it depends. If the sound is bad, it's horrible, and sometimes sound is good. But I think generally, if it's very loud, it's not comfortable.
Yeah. Yesterday, one student said me, she told me that it depends on how much alcohol you drank. Yeah, it's like it's alcohol consuming. Yeah, if you drank a lot, it's normal. Yeah, if you are sober, then it's hard to tolerate. Yeah? And it's okay. Yeah, because you know, alcohol works as suppress our nervous system, and therefore, of course, every loud sound becomes more quiet for us. Yeah. So, and yeah, but yeah, live rock concert is okay if you do not stay near the sound source. It means if you go and stay and take your position somewhere close to the sound source. Yeah, for example, 2 or 3 meters near the sound source, then it becomes absolutely intolerable sound, because it's about 120 130 decibels loudness, and therefore it becomes intolerable. Yeah, it's is close to threshold of pain. Actually, these red ones already illustrate the threshold of pain. What does it mean, threshold of pain? It means the sound becomes too loud, or the level of the sound amplitude becomes too high, then you can't withstand it. You feel the pain in your ears and you want to go away or switch off the sound source. Yeah, and if you can't switch off and you can't run away and you need to stay there, then at the moment your eardrums could be damaged and you can get irreversible hearing system damage. And of course, nobody wants it. And that's why I suggest you, if you, for example, use chainsaw somehow, or you need to go to, of course, you don't need, it will be quite interestingly if you go to live rock concert and use big earphones, because that's why you go to live rock concert, in order to take a rest, in order to relax, in order to enjoy it. But if you go to live rock concert, I suggest you stay further from the sound source. You can save, your hearing system will be in safe. Yeah, and if you go further, screaming, you see screaming baby. Screaming baby, here is a good example. Yeah, screaming baby. And when he screams, it's pretty pretty hard to tolerate. And then I want to go to another room. Yeah, now it's he's this is Carlos. Yeah, he's very silent now. But when he starts screaming, then it's I want to go away. Yeah, my wife can tolerate it more. This sound is something intolerable for us, and if it's constantly for a long time, then it's bad. It then becomes, yeah, you know. Okay, and if you go further, rustling leaves. Yeah, from my point of view, it's a most pleasure sound for me. It's like you can even meditate, or you can even relax under the rustling leaf. I enjoyed walking in the autumn through rustling leaves, how they create a good sound, normal breathing, and so on. This is like how it all of them. Yeah, like level of sound, intensity, power per square meters. Yeah, like power per square meters is intensity, some amount of sound on the some amount of sound on the area. Yeah. So, and here again you can see hearing or area where we feel comfortable. It's until the 120 decibels. Here start to screaming. You hear? You can enjoy now. Okay. Then over 120, 140 decibels, it's already discomfort zone. Yeah, you want to switch off, or you want to go away, or you feel unpleasure, like not so good. Yeah, and you want discomfort. Yeah, and over the 140 decibels, it's already pain area, which, as I told you, it's create unreversible changes for our hearing systems. This is an audiogram. You can see how does it looks like. Actually, audiogram, it means this is what doctors do when he or she checks your hearing system. Yeah, you just switch the frequency. For example, at the beginning, let's from the 40 hertz, and ask you, are you hear the sound? And if it's and slowly adjust the level of sound, it means the loudness or volume. And at the moment when you say yes, I hear, the doctor gives a point on the graph. Yeah, and therefore, if you go through all frequencies, then it first of all slows down. Then our audiogram has a wide maximum over the 2000 or 5 till 5000 hertz, or 2 until 5 kilohertz, and then it slowly goes up. And this is a normal audiogram. You can get it in today's lab work. So yeah, and final video will be about our hearing system. Yeah, here you can yeah, you can read actually what's happening. I do not repeat it here. You just can read what's happening, and I'm absolutely sure that you, as a future medical professionals, you will study more and more during your study year, and that's why I just included here. But this is not the physical meaning of sound. It's just how sound can, how we can hear. It's important, yeah, from medical point of view, especially. But let's have a look at this amazing video, which shows how we actually hear the sound and what's happening in our. And actually, it's how complicated such systems are. Yeah. I will share the sound as well.
They pick up sound waves and change them into information that the brain can interpret, such as music or speech. Sound is a pressure wave that can vibrate either quickly or slowly. Slow vibrations produce deep sounds, while quick vibrations produce high-pitched sounds. Sound enters the ear and is directed through the ear canal, where it first reaches the eardrum. As the eardrum begins to vibrate, it sets the ossicular chain in motion. The ossicular chain consists of the hammer, anvil, and the stirrup. Sound vibrations move along the ossicular chain and into the inner ear. Within the inner ear, the cochlea plays a central role. It is here that the mechanical energy of sound is converted into complex electrical signals, which are then passed on to the brain. In simplified terms, the cochlea is a spiral-shaped tube filled with fluid. Sensory cells, also called hair cells, line the entire length of the cochlea. These hair cells have varying degrees of sensitivity for the detection of different tones or frequencies. This allows the ear to perceive the entire spectrum of sound. The change from mechanical vibration to electrical pulse is a complex process resulting from the movement of hair cells in the cochlea. Along the entire length of the cochlea, the hair cells are arranged like the keys of a piano. Hair cells located at the base or lower region of the cochlea are responsible for high frequency, while hair cells at the apex are responsible for the low frequencies. As the fluid in the cochlea is set in motion, it causes a corresponding movement of the fine structures on the surface of the hair cells to take place. These movements cause tension differences which produce electrical signals that are passed along the hearing nerve to the brain. The auditory cortex of the brain interprets this information as sound, for example, as music or speech. The entire chain of events, including the various steps that convert sound waves from the environment into information that the brain can interpret, happens so fast that individuals can hear sound both continuously and instantaneously. Within this complex chain of events, there are a number of factors which can cause an individual to experience hearing loss. A loss of hearing can range from a mild to moderate hearing deficiency to a total hearing loss. In general, there are three main types of hearing loss which differ from one another depending on the part of the ear that is affected, be it the outer, middle, or inner ear.
Yeah. With this video, you can actually hear
Ears
that
are constantly active. They pick up
we hear the sound with the brains, yeah, with the brains, and this is an important fact, yeah. We perceive the sound actually with the brains, yeah. I will switch, yeah, okay. So and let's go further quickly. We don't have a time. Actually, the long lecture for you. You can see here audiogram which shows actually this graph show if you look to the left side, it shows the level of loudness which is normally we need to hear if we have normal hearing system, if everything works properly, yeah, then we can hear even 10 decibels, yeah. It's absolutely amazing level of sound. Is just little, yes, it's close to silent, but we can hear it, yeah. Mild hearing loss, we can hear, our patient can hear only 20 decibels. Moderate hearing loss, only 50. Severe hearing loss just is 70. And if you go back and look to this chart, you can see that 70 decibels, it's here is not written, but sorry, it's another presentation, but no, yes, here, yeah, 70 decibels, it's about city traffic, yeah. You know, it means that you can easily conclude that if our patient has severe hearing loss, yeah, it means he don't hear anything except screaming baby, lawnmower, chainsaw, car horn, live rock concert, jet engine, and gunshot. But he or she do not hear conversation, rainfall, library, whisper, rustling leaves, normal breathing, and so on, yeah. And that's the way. And profound hearing loss, it's over 18 decibels, yeah. And hearing loss can cause it by factors exposure to loud noise, sorry, yeah. That's why I told you avoid from loud noise, yeah, especially extreme loud noise. Natural aging, heredity, head injury, ototoxic medication, either illnesses. In this final point, you can see mechanical damage of receptors in a cochlea. Intact cochlea and damaged cochlea. How does it look like? It's a microphotography of scanning electron microscopy. So, and finally, we will come to our lab work today. We need to create our own audiogram. Let's have a look, yeah? If you open audiometry protocols from the e-studies,